What is up, Algebros? This is Algebra 1, Lesson 8-7, which is factoring special products. So before we jump into today's, just real quick, let's remember a few things. First off, can we just factor this one? Since there's three terms, we know it's probably going to, if it's possible, factor into two binomials like that. Since the first one just has a 1 in front of it, we know this is going to be an x and an x. And then, since this last term is positive, we know these both have to be the same sign, and since both have to be the same, we can look at this, and they both have to be negative, so I can go and put in the negative signs. So then I just need to find factors of 6 that add up to 5. Factors of 6 that add up to 5. So factors of 6 be 1 and 6, 2 and 3, and that's all of them. Notice 1 and 6 add up to 7, so that's not it. 2 and 3 add up to 5, so that's the combination I need. So here we go, 2 and 3. So this would be the factored form of that. Okay, so that's what we're doing, is we're going to be factoring today. But before we get into these special factors, let's just go ahead and multiply one of these. This one right here. Remember, we used to say everything in this first one times everything in the second one. Some people use the FOIL method. First, outer, inner, last. So the first ones would be x times x, which gives me the x squared. And then the outside, right, which is this one times that one, is going to give me minus 3x. And then the inside ones, which gives me plus 3x. And then the last ones, so that gives me minus 9. Now, we need to combine like terms. Notice I have a 3x and a positive 3x, so it just gives me x squared minus 9. So notice, normally we end up with something like this, with a trinomial, but on this one, the special case, we end up with just 2, a binomial. And if you look up here, notice this is x plus 3, x minus 3. So if we have something in this format, when we multiply it, it comes into this. So what if we want to go the other way? Well, one way to look at this would just be to think of this like this, saying x squared plus 0x's minus 9. So then we could still apply that same rule that we did earlier. That has a coefficient of 1, so it's going to be x and x. And I need to find factors of 9, which is 1 and 9 and 3 and 3. But this time, since this is a negative, my signs have to be different. So I'm going to find factors of 9 that subtract to give me 0. So 1 minus 9 or 9 minus 1 usually gives you plus or minus 8. But 3 minus 3 gives you 0. So I want to use those 3's in the 3. And so one has to be positive and one has to be negative. So this is how we'd factor that one. Now hopefully we can start to recognize this is a perfect square because x times x gives me that x squared. And this is a perfect square because 3 times 3 gives me 9. And they are subtracting. And that brings us to the title of this special case, difference, meaning subtraction, of squares. So this is a perfect square, that's a perfect square. So let's just look at these real quick. There's 4 of them here, and we need to say yes or no. If yes, we're going to factor them. Are these a difference of squares? So is 81 a perfect square? Yes, it is, because 9 squared is 81. And is c squared a perfect square? Yes, because c squared is c squared. Okay, so I would say yes for this. This would factor into 9 minus c and 9 plus c. You could have also said, like switch those, said 9 plus c and 9 minus c. Those are the same thing. So it's just kind of the square root of this one in the first part, square root of the second one in the second part. They're the same, but one's positive, one's negative. Now, is this one difference of squares? Well, is 1 a perfect square? Yes. Is 25 a perfect square? Yes. Is y a perfect square? Yes. So initially I want to say yes, however, it's not a difference, that's a sum of squares. So in this case I would say no, and I don't have to go any further. Okay, what about this next one? Is 36 a perfect square? Yes. Is n squared a perfect square? Yes. Is m to the 4th a perfect square? Yes, it is, because m squared times m squared gives me m to the 4th. But what about 27? No, that's 9 times 3, so that does not work. So I'm going to say no on this one. What about this one? Is this a perfect square? So is 36 a perfect square? Yes. G squared a perfect square? Yes. H to the 4th a perfect square? Yes. Because, so this would be 6 squared and G squared minus H squared gives me H to the 4th. So I'm going to say yes, this is. So it's going to factor into 6G plus H squared and 6G minus the H squared. Alright, so the next thing we're talking about is perfect square trinomials. So before we start factoring them, let's just look at what they would kind of look like and see if we can find a pattern here. So if we're given something like this, x plus 4 squared, it's being squared, that means there's 2 of those being multiplied with each other. So I'm going to say the first x times x is x squared, x times 4, so that's plus 4x, plus 4 more x, plus 16. So this is going to give me x squared plus 8x plus 16. Let's try another one here. Same idea now with this. I have the 2x minus 3 squared. So that means it's going to be 2x minus 3, 2x minus 3. There's 2 of them. So I'm going to say 2x times 2x. This gives me 4x squared. 2x times a negative 3 gives me minus 6x. Negative 3 times negative 2x gives me negative 6x. Negative 3 times negative 3 gives me positive 9. Combining those like terms, I end up with 4x squared minus 12x plus 9. So let's see, first off, do we see any similarities between these? Seems like they both have an x squared. This one has a 4 in front of it, that has a 1. This has a 16 and a 9. Well, I noticed that 16 and 9 are both perfect squares, and so is this, right? And this is a perfect square. But I don't necessarily see a correlation here between these center ones. So let's just do a generic one. If I had ax plus b squared, what would that come out to be? So ax times ax would be a squared x squared. Ax times b would be abx. B times ax would be another abx. And then b times b would be plus a b squared. If I combine those two terms, since they match exactly with the variables, I'm going to end up with an a squared x squared, plus, since there's 2 of those, would be 2 ab x's, plus a b squared. Now in general, we won't give you something like this to do, but notice this is a perfect square, this is a perfect square, and this middle one is 2 times the square root of those two, right? So see, that same thing applies here. What's the square root of 4? Square root of 4 is 2. Square root of 9 is 3. So what is 2? That's that 2 right there. Times 2 times 3. 2 times 2 is 4, times 3, that gives me 12. So notice that matches that number right there. Same idea here, I'm going to put a 2. Again, that's from that, following the pattern here. Then the square root of 1 is just 1. The square root of 16 is 4. 2 times 1 times 4 gives me the 8, which again matches there. So now we're going to just see if we can identify that. If we're already given the trinomial, is this a perfect square? So first thing you want to check is this a perfect square, and is that a perfect square? If it is, then you keep going. If not, then you just say no. 16 is, because that's 4 times 4, and 9y squared is because that's 3y squared, or 3 times 3 is 9. So we're going to, so this is going to be 3, and the square root of that one is 4. So multiply 3, sorry, 2 times 3 times 4. What does that give me? 12 times 2, which is 24. Does that match that one? It does. So then what we need to do is go ahead and factor that. This is going to factor into the 3y, so y, plus 4 squared. We use the plus right here because this is a plus. If that was a minus sign, then we'd use a minus. So we're going to do the square root of that, and it factors just like that. Feel free to expand it and check that. For this next one here, is 25 a perfect square? Yes, it is. Is this a perfect square? No, it's not. I forgot to say yes over here. So yes. So this one I would just say no, because that's not a perfect square. Okay, so let's kind of bring everything that we've been learning in this chapter together a little bit with factoring. So when we go to factor something, the first thing I want to do is see if there's a common factor that we could factor out of every term. Once we've done that, then you can move on to see if there's any special cases of the ones we've kind of talked about today, because those are a little bit easier to factor. And then after that, see if there's anything we can factor beyond that using our normal method with the trinomial or by grouping or something like that. So first off, do these two have something in common? They do. They both have a 2 as a factor. So I'm going to write 2 on the outside. What's left over is going to be a y to the 4th, and then 2 times 25. Okay, so that's the greatest common factor. Now I'm noticing that these are both perfect squares. That's a y squared. It's a 25, or 5. So that means this is going to factor into 2. Difference of squares, this is going to be a y squared plus 5, and a y squared minus 5. And I want to keep looking at these. This is not a difference of squares. This one almost is, but that's not a perfect square. So this is as far as it's going to factor here. Okay, this is the next one here. Let's see if we can find anything in common between all 5 of them. These 3 have an m, but that one does not. These ones have a 5 or a 25, but these do not. So I'm not seeing something in common between all of them. And notice I have 4 terms, so this is going to be the factoring by grouping. So let's see if we can kind of group some of these. I'm going to group these 2 together and plus those 2 together. So these first 2 both have an m squared in common. What's left over is a 2 and an m. I'm going to say just plus 1 there. So if I multiply this times this, it'd give me that. This times this, it'd give me that. Then I'm going to say plus, what do both of these have in common? They both have the negative 25. So I'm going to say minus 25. What's left over is 2m plus 1. Now I'm looking, this and this match exactly, so I'm going to factor that out. So I'm going to have the 2m plus 1. What's left over is that m squared and then minus the 25. And I think I'm done, except I've noticed that this is a perfect square, kind of like we had here. So we're going to factor that out a little more. So I'm still going to keep that 2m plus 1. I'm going to have an m plus 5 and an m minus 5. Because m is the square root of that, 5 is the square root of that. So this is going to be my answer. And then over here, oh look, these are both perfect squares, because one's a perfect square, 16 is, and so is y squared. So this is going to be 4y squared plus 1 and 4y squared minus 1. Okay, now I'm noticing that this one on the right is still a perfect square, because 4y squared is still perfect square, and 1, so is 1. So I'm going to leave this 4y squared plus 1. This is going to factor into the square root of 4 is 2. The square root of y squared is y. The square root of 1 is 1. So I'm going to say plus 1. It's going to be 2y minus 1. And this would be my factored form. If you haven't noticed already, your homework is on page 543. You're going to do 1 through 16 all. Good luck, guys. You're going to do awesome.